In this tutorial video, I'm going to go over the oxidation simulation in the PuMA software. Before I get into it too much, the oxidation simulation is fairly detailed and will require a lot more than just watching this tutorial in order to understand. To understand the oxidation simulation better, it's recommended that you read the manual that comes with the software, which is in the PuMA V2.1 folder. Under Docs, there should be the PuMA user manual. Now in here, there should be a section 3.7, which goes through a lot of the theory of the oxidation model, and then finally there should be a section at the end, starting at page 104, that goes through what each of these options are and how to run the simulation properly. But perhaps most importantly, the Microscale Oxidation model theory section in section 3.7 should really be read prior to trying to run any of these simulations. There are also a number of journal articles that have been published based on our work, and these can be found in the references. So moving on to running the simulation itself, it's assumed that you will have run the installation instructions already, and then PuMA can be launched by simply typing in PuMA from any terminal window. The first step is going to be to load a three-dimensional TIFF image or to generate an artificial geometry. For the purposes of the tutorial, we'll load a 3D TIFF image. We're going to take a smaller sample since we are running this on a laptop. I'll do 256 by 256 by 511 with a voxel length of 0.65. The grayscale threshold for this image is anywhere between 87 and 90 is an appropriate value. And as you can see, this is what we have imported, which is a subset of the carbon fiber material that comes with the PuMA distribution. To run the oxidation simulation, move over to Oxidation Simulation tab. This is really separated into simulation inputs, which is the inputs that the simulation will use, the output options, which sets what you want to output, and then the runtime outputs from the simulation itself. To populate these with some reasonable values, you can go to Oxidation, Load Inputs from File, and load the example input file. The first simulation input is simply the temperature. The temperature is one of the main parameters that's in charge of controlling the reactivity of the carbon fibers, which will determine what regime the oxidation is occurring. The pressure is pretty self-explanatory. It relates to the total number of particles that are used in the simulation. The delta R is the mean free path of the particles. So in this case, we're using 2 times 10 to the minus 6 meters, which will be just a couple voxels here. So it should be in more or less the continuum. Gamma is the sticking coefficient, which is left at 0.8. The diffusion coefficient is specified here. This can be computed using, for example, mutation ++. The mass fraction of O2, the molar mass of the gas, these two are currently set to be the value for Earth, except I think this might be 28.97, but it doesn't matter for the purposes of this tutorial. The size of the buffer zone is the size in voxels above the domain for the reservoir of the particles. So I'll show you what that means. If we go into visualization options and set it to display the buffer zone and display the particles, and we create a simulation, press visualize. Let me change that. Press visualize. We see the reservoir on top. The blue shows the buffer zone, and if we zoom in, we can see the particles that have been distributed on top. Currently there are 7,000 particles. So we'll have to play around with the parameters here, since that's not nearly enough particles. For the purposes of this tutorial, I'm not going to be using physical parameters. I'm going to be adjusting these to make it just more easily understandable for the tutorial. So in this case now we have 70,000 particles, and you can see they're now displayed on the top. So to keep going down here, the size of diffusion length is a length between the top of the buffer zone and the top of the material, and as you can see here, it's 0, which means the buffer zone will be right at the top of the material. That can be set to be higher, but typically this value is left blank or just left at 0. The moles of O2 per Walker is pretty self-explanatory. This just decides how much physical oxygen is represented in each of these particles. The density of the carbon fibers is typically 1700. If we're using physical conditions, it's about 1700. For the purposes of making this run very quickly, I'm going to use a very artificially low density for the carbon fiber. These two options have to do with whether you want to create a matrix around the carbon fibers for the oxidation. Typically, for the materials that we're studying, there is not usually just carbon fibers. There's usually also a carbonized phenolic matrix around those fibers. This can be set to be just the fibers, or it can set to be a dispersed phase, which I can show an example of here, where in brown you see the resin. This can also be set to be a coating around the fibers, which I'll now show, where the brown around the fibers represents the resin. I'll go ahead and leave that on for the simulation that I'm going to show. Finally, the reactivity ratio, which is a ratio of the reactivity of the matrix compared to the fiber. So 1 means that the reactivity of the fibers is the same as the reactivity of the matrix. 10 means that the matrix is 10 times as reactive as the carbon fibers. Density of matrix is self-explanatory. I'm going to leave it the same as the density of the carbon fibers. Actually, I'll decrease that to slightly lower. And then the matrix coating radius, which is the radius around the fiber that the matrix coating occurs. So the number of time steps is pretty self-explanatory. It's the total number of time steps that are going to be run. You can see what the actual time increment is here. The megastep increment is used for the parallelization, and that means that each particle is going to run totally independently of each other for that number of time steps. We'll lower that slightly. The buffer check increment is the amount of time that the simulation runs, the total number of time steps, before the simulation checks to see whether the buffer zone needs to be moved down. When the buffer zone is moved down is in the event that the oxidation has occurred, enough of the material has gone so that there's no more material at that phase. So for example, if it's oxidized all the way down to here, the buffer zone will go down accordingly, and it'll check that every 500 time steps. The number of threads I'm going to set to 4, which is just used for the parallelization. In terms of output options, if this is checked, it will visualize the simulation in real time, and you can set the number of steps between the visualizations. I'll set that to be 1,000. And then make movie simply means that it's going to then save those files. It'll save those files to in the runs folder under movie images. But obviously there's nothing there, but if this were checked, it would save those to that location. If rotate is checked, then it will, every time it saves an image or renders an image, it will also rotate by whatever step you put here, and that rotation is in the Z direction, but we're going to leave that checked off. Save simulation data will save the data in the oxidation statistics folder. It'll save the porosity and surface area as a function of depth and other useful simulation data. Save TIF stacks will save the oxidized TIF stack between the a certain number of oxidation steps. Save triangles, same thing, it'll save an STL file between each number of steps. The triangle outputs will be here, the oxidized TIF stacks will be in this folder. We're going to leave that off to increase the speed of the simulation. Going on to the runtime outputs, the time increment is the amount of time in seconds between each time step. The fiber reactivity is a value in meters per second, and that is just the reactivity of the fiber. It's explained more in more detail in the theory section in 3.7 of the user manual. The diffusion coefficient is repeated from here. If this is left blank, it'll come up with an approximate value for it, but it's recommended that that be computed in Mutation or some other software. The number of walkers and the number of walkers that are in the buffer zone is shown. So as the simulation progresses, the number of walkers in the buffer zone will stay the same since this is the reservoir, but a number of particles will percolate down into the material, especially depending on the conditions that are used. The molar volume of, the buffer concentration is the concentration in kilograms per meter cubed of the oxygen. The carbon molar volume is fairly self-explanatory. That relates to the Greyscale Reduction, which means for every sticking event, what the chances are, or not the chances, for every sticking event, how much carbon is removed. So how much grayscale is removed. A full solid carbon voxel has a value of 256. So this means that approximately 11 or 12 collisions or sticking events have to occur in order for a voxel to be completely removed. The same thing is true of the matrix, except in this case it's 5 or 6 collisions need to occur. Sherwood number and reactivity contrast mostly have to do with the analytical solutions, which are explained both in the user manual and in the related journal articles. The buffer zone min and max are the current minimum and maximum positions of the buffer zone. So it is currently from -20, which is this point here, to 0, which is the start of the geometry domain. The maximum sticking probability basically means that for every particle that hits a carbon surface, it has a 29, or carbon fiber surface, it has a 29% chance of reacting, and for every time it hits a matrix surface, it has an 80% chance of reacting. This is based on the reactivity values, which are based on the temperature and the reactivity contrast that was specified here. We're going to go ahead and run one of these simulations. It may take a little bit too long for anything visible to show for the purposes of this tutorial, but we'll let it run for a few time steps and see how long it takes. I might fast forward the video to the end. So now that the simulation has finished those 20,000 time steps, it hasn't finished oxidizing, but it's good enough to give you an idea of what the oxidation simulation does. As you can see, the matrix recessed slightly faster than the fibers, and it exposed the fibers which are reacting slower. There's a lot of aspects to this that I didn't get into in this video. I really recommend that you read the user manual before trying to run any of these oxidation simulations, but this video should hopefully give you just a basic idea of how these simulations are run. If I think that concludes the oxidation simulation tutorial of the PuMA software.